Okay, we are back here. It's Friday, February 12th, chapter 20, starting carbonyl additions, organometallics, and hydride reducing agents. No class on Monday, President's Day. Woohoo, it's a holiday. But Tuesday is class. So the old switcheroo that only BYU can do, Tuesday becomes a Monday. So those are the sections that should come there. And check your other classes. Don't forget about your other classes. It's a Monday schedule on Tuesday. And then, of course, we have class on Wednesday. So you don't really get much of a break next week, but you get the longer weekend. So don't come on Monday. We won't be here. There won't be a video. Um, Quiz 4 was originally, I think, on the schedule for this week, but we pushed it back. Yeah, so it's on Thursday now officially. Questions on any of this schedule-wise? I think we're okay. Um, let's look at the outline up above here, Nick, for chapter 20. And yeah, a lot of detail here. There's a lot of substrates. The reagents, though, will be quite similar. Hydride reagents, hydrogen with 2 electrons as a nucleophile, and carbon as a nucleophile, carbanions as nucleophiles. So there, the reagents will be pretty consistent, and the substrates will be quite diverse. It's actually the opposite of electrophilic aromatic substitution, where we saw a diverse set of reactions, the 5 and a couple of those peripheral things. But benzene was the key substrate, right? But now the substrates are going to be kind of diverse here. We'll look at carbonyls in general, and the nucleophiles, how they come in, give a tetrahedral intermediate. And with aldehydes and ketones, that's the end there. But with derivatives of carboxylic acids, you have a potential leaving group there on the tetrahedral intermediate. So that gives us diverse products there, depending on what this X group is. We already talked about derivatives of carboxylic acids, so some of that should be okay. If we're adding hydride, that's a form of reduction. And we'll review oxidation here later on. If we go the other way and take an alcohol and go back to a carbonyl, that's a form of oxidation. So these reagents here will be sodium borohydride and lithium aluminum hydride. We'll say a little bit about chiral or asymmetric ones. We'll have some variations of those reagents, the lithium tri-T-butoxy aluminum hydride and dibal, diisobutyl aluminum hydride. Oxidations, this is purely a review, except maybe the silver oxide there. Then the organometallics. This is probably the most important reaction, I think, to make carbon-carbon bonds with a carbon nucleophile. These are the organometallics. There'll be organomagnesium reagents, the so-called Grignard reagents, in honor of Victor Grignard. There it is. We'll look at organolithiums also, organomagnesiums, adding to different carbonyls to give different types of products. We'll also add to epoxides and carbon dioxide, enones, but here's the deal. Here's the formation of the Grignards from the halides. And there, it's this carbon nucleophile, you see, that can add. Then we quench with water or dilute acid to give the alcohol products. Protecting groups, sometimes we want to eliminate the acidity of an alcohol, because any protic source here can protonate an organometallic. So to make it stable to base or stable to the organometallic, we first can protect. We'll talk a little bit about protecting groups. And then the cuprates, dialkyl copper reagents add to enones to give substitution or addition, we should say, at the beta position to give new types of ketones there. And a little on synthesis and the planning and how they're used. Now, speaking of synthesis and planning, I like to show up front some of the applications here. And this can be a little overwhelming, all the reactions here. And some of them we haven't covered, so you don't know. But I'll try to focus you in here. Here's a vinyl Grignard, adding to that aldehyde to give this alcohol product. That's a reaction we'll cover. And then taking this ketone to an alcohol, and antioselectively, actually. You could do that racemically with sodium borohydride or lithium aluminum hydride. We got a couple protecting groups. I think that's it. There's some SN2 chemistry in there too, I think. Yeah, we got LAH here, reducing the ester. There's other derivatives we can reduce to the alcohols. Well, there's some others in there. Oh, these are used to treat asthma. And some of you maybe have taken Flovent or albuterol, Ceravent here. This is the longer acting one, has a longer chain here, 12-hour half-life in the body. This is a shorter, more emergency inhaler type thing, albuterol. But you can see how they're made here. Some SN2 chemistry. Where's the reduction stuff? Oh, there it is, lithium aluminum hydride to go from this ester ketone to the dialcohol. Was there any others there? Oh, celtamivir. Yeah, we won't get into that. We did that before with the diels-aldehyde. I don't think there's any reductions or Grignards in there. Okay. But we'll get to that part later, the asymmetric thing. All right, let's go to the board here and see what we need to know about chapter 20. And I like to compare this, give you the mechanisms up front, and hopefully the mechanisms help you understand and keep track of these reactions better, the commonality. These are all carbonyls, right? Carbon, oxygen, double bond. These are aldehydes or ketones, right? So either a hydrogen here or two carbons for a ketone, okay? Now, if we add a nucleophile there, there's our partially positive carbon, right? Flow the electrons in, flow the electrons up. That step is common to all the reactions in this chapter and some others coming up, okay? Now you get to this intermediate. Notice it's sp3 hybridized now. We call that the tetrahedral intermediate, okay? That's common to all these reactions, very common to carbonyl reactions. That tetrahedral intermediate then can be quenched with water, right? We can just protonate that because that's basic, that's an alkoxide. And that's the product. That's the end of the road for aldehydes or ketones. And what do we call that? If the nucleophile here was hydride, we call that what? A reduction. Because we just added hydrogen across there, right? And there when we protonated. So there's our two hydrogens doing a reduction. If we go the opposite way from an alcohol to a ketone or aldehyde, that's an oxidation, right? So in this direction, it's a reduction. In the other direction, I think you're familiar with oxidation, meaning adding oxygen or taking away hydrogen, okay? And we know that with the chromium reagents. We'll review that also today. Now, the derivatives of carboxylic acids here. If X is OH, that's carboxylic acid we just covered in chapter 19, right? But we have other derivatives, chloride or an ester, and there's a couple others, right? So I'm not going to list all of them there, but that's an X group. That's a heteroatom on the side. That's different than aldehyde or a ketone, right? Because once you add the nucleophile, and that part's the same, okay? Here's the difference, though. Well, it's similar in that it's a tetrahedral intermediate as sp3 hybridized. But what do we have here? We have now a leaving group. Exclamation point. That's going to change things, okay? Because the tetrahedral intermediate can break down like this and give us back a carbonyl with that nucleophile in there. Now that nucleophile, you know, it's going to be carbon or hydrogen. And so, you know, it could be an aldehyde now, or it could be a ketone. So potentially you could have more nucleophile adding, okay, depending on the conditions in the reagent. We'll see that with esters and acid chlorides, with the Grignards, and also with the hydride reagents, okay? You can go all the way from the derivative down to the primary alcohol in that case, okay? If this is two hydrides here, okay, we'll have to see. But the mechanisms are the same, okay? Look for the commonality. Don't view the mechanisms as just an extra hassle. It'll seem that way sometimes when I start plowing through them today. But use the mechanisms to hopefully correlate and keep track of the reactivity here. Okay, let's start out with the simplest one, sodium borohydride. And what do we need to know there? We're going to take an aldehyde. Oh, let's take benzaldehyde here. And here's our reaction. Sodium borohydride, okay? The reagent, you know, what is it? Well, it's 4 hydrogens on there, plus charge on sodium, negative charge on boron. And then we have to add water. Now, sometimes we just show the water below the arrow. We should show a slash because it's added separately. If the water or the proton source is in there, sometimes we can generate hydrogen gas instead, okay? We want the hydride to react first with our carbonyl and then add in the quenching agent. And what's our product here? Well, it's benzyl alcohol. Okay, so can you see where things are? We've got one hydrogen already here. What is borohydride? Let's draw it all out in its glory. Okay, so sodium is plus charged. Metals are always plus. Okay, and that helps you. What is the tetrafluoroborate charge then? It must be what? -1. Okay, which means what? It's a salt. Okay, it's a solid, high melting material, which also means this hydride can come off. Okay, push the electrons up here. So now we're doing the mechanism, right? So we'll have O minus now. Sodium's up there to be the counter cation. And what? The other hydride's on there. So let's circle that one that came on there, okay? And notice it came off with its pair of electrons. So what's the byproduct of the boron? Well, it's borate, BH3, okay, with an empty orbital there. So we've got some other reactions here to show you. How about this aldehyde? Same thing, sodium borohydride, water. What are we going to get here? We're going to get the primary alcohol. And that's another thing to keep track of. Aldehyde to primary alcohol. Aldehyde, primary alcohol, okay? Because there was a hydrogen on there to begin with. Now there's two hydrogens on there, okay? It's a way to help keep track of it. What about ketones? How about acetone? Well, there's two carbons on here, right? So if we add hydride here, what are we going to get? We're going to get secondary alcohol. So ketones are a little bit different, right? Okay. Now, just when you think, oh, you know, this is pretty simple. I can handle this. How about this? How about if we have cyclic ketone? You know, let's have another group on there, a methyl group at the 4 position. Now, I'm drawing that up for a purpose. That's not a stereocenter. But if we consider this top face here, our hydride could either add from the top or the bottom face of this ketone, right? And guess what? It does both. So sodium borohydride here can go to this. If it adds from the bottom face, look at that. You can get the cis product. Okay, there's where your hydrogen came from. So considering the mechanism, right? Plus what? It could also add from the top, which would give us the alcohol down. And yeah, this would be what the trans product. These are both achiral still, okay? But they're what? They're diastereomers of each other, okay? They're stereoisomers that are not mirror images, okay? So they're technically what? Diastereomers. And that shows the complexity of this. This can become stereogenic and be important for stereochemistry. We'll see some others that are chiral isometric. What I want to point out now is all of these reactions with sodium borohydride can also go with lithium aluminum hydride. Okay, lithium aluminum hydride has an acronym which is nice, LAH. Okay, in fact, LAH is by far much more aggressive reducing agent. If you put in the water or even have a trace of water in the presence of LAH, it will start to warm up and fume and maybe catch on fire. Okay. Sodium borohydride will be specific for aldehydes and ketones, whereas LAH will do all the other carbonyl derivatives. Okay. So very similar reactivity, also a hydride. Okay. Why is it more reactive? Usually a student has a question. The book doesn't explain that. Why is LAH so much more reactive, more aggressive reagent, and why can it catch on fire? I've seen it happen actually on a humid day. One of my colleagues in the lab was weighing out about 100 grams of LAH on the balance. It was a summer, humid day, a lot of moisture in the air. I looked over at the balance and he kind of walked away for a while and had this pile of LAH sitting there and it started to smoke. I was wondering, what do you got on the balance there? Oh, it's LAH. I'm getting ready to do this reaction. You see it's starting to smoke? And we were looking at it, and all of a sudden sparks started shooting out of the top of the pile. So this reagent is very aggressive. Why? Why is it so much more reactive. Sodium borohydride won't do that. Okay. Yeah. Yeah. So aluminum is and boron are in the same time. It's the first row of the main group block. So it's got 3 valence electrons. Yeah, you should verify the negative charge, but aluminum's bigger. So these are longer bonds. They're less stable. Okay. These come off more easily. Boron's a smaller element. It's held more tightly. Okay. Some people like to point out that lithium is more or less acidic than sodium. That's not quite true. The lithium and the sodium are just counter cations. I think the main thing is the length and the stability of the metal hydride. But that's a nuanced thing. Don't worry about that. All right, let's get into the mechanism a little more. We've got part of it up here. I want to point out a little bit more on the mechanism because right here you still have borane. There's still 3 more hydrides. In fact, when you use sodium borohydride, you only need 1/4 of an equivalent to get a high yield for the reduction. So it means what? All 4 of those hydrogens can go on there, okay? So let's see what else could go on here in our mechanism. Well, we could add the intermediate benzoxide, right? The O- into borane, BH3, and get this. Oh, no, it's a 3, sorry. Already added 1, right? And then what can we do? Well, you can add more to this, right? So another hydride can go on there. And what would we get then? We'd get, you see, another reduced thing here. And we'd have what we could have, boron with the other alkoxy group. And now there's 2 on there, you see. And then we could do another one. We could do this 2 more times, actually, until we get what? We get 4 of those on there, okay? So we can keep adding these. I'm sorry, so this is after addition here, and then I left out part of the mechanism. That has to come back and grab the boron with now 2 on there. I think you can see how it's done. It can go to the tetra alkoxy borate. And then how does the water work? Well, we have a proton source, right, on the water. So you can just imagine the oxygen borate bond coming and grabbing that. And you see that gives us the alcohol product, okay? The boron ends up as boric acid. Eventually, you got to push some more electrons. Don't worry about that. That's inorganic stuff. But I like to at least show enough of the complete mechanism to show how you can add multiple hydrides there. The key step is up there, okay? The flow of the hydride into the carbonyl, okay? Recognize, though, that it can be excess of that way. All right, what I also like to point out here is that you can have some chemoselectivity. Here's a compound with 2 double bonds, right? 2 types of double bonds. Now, what we saw before for reducing things was hydrogen and palladium, right? We can do this. Hydrogen palladium, that will go after the nonpolar alkene, okay? That matches the polarity here, and the hydrogen adds first to the palladium. That's a 351 reaction, right? If we let this go with more time and pressure and heat, time, pressure, and heat, we can actually go to the fully reduced thing here. But it's very easy to stop here at room temperature with modest pressure. But both carbonyls can go away with palladium and hydrogen. Well, what if we just want to reduce this one? Well, we use sodium borohydride. Okay, and quench with water. And what do we get? The alkene stays behind, and just the alcohol gets reduced. Okay. These are examples of chemoselectivity, where one functional group can be reacted in the presence of another, okay? Depending on the reagent. These are polar reagents, right? The hydride's charged. That's matched to the polar carbon-oxygen double bond. Whereas the nonpolar alkene is matched here, to this. But it's the same concept. The pi bond's gone away, right? Went from sp2 to sp3 hybridization. Okay, LAH. LAH can do all the reactions we've shown before, and it can do these. So if we have carboxylic acid, LAH, and again, you add the water later, you can go to the alcohol, okay? And that's a different reaction now. That's not an aldehyde or a ketone. And what did we add? We added 2 equivalents here of hydride, okay? So that will be different. Sodium borohydride will not do that with a carboxylic acid. LAH with a ester will also go to the alcohol product, okay? So you can take benzoic acid with LAH, and you can go to benzyl alcohol. So there's a connection between benzoic acid and benzyl alcohol. Let's do a little more complicated ester and look fully at the different products. So LAH, and again, after quenching with water, what do we get? We get the benzyl alcohol again here from the ester. Well, what happens to this part of the molecule? Well, it'll come out of that mechanism up at the top. Once it adds here and the tetrahedral intermediate comes apart, it will have also the alcohol that corresponds to the other side, what was on the carbonyl. So with LAH, we have a more variety of reduction reactions, and we get a little bit different products that we'll have to keep track of on the mechanism. But sodium borohydride with these, no reaction, okay? Now, another thing to point out here with these reactions is this. If you have a ketone here with 2 different groups on the side, what can occur here? Well, the reduction can occur either with sodium borohydride or lithium aluminum hydride. But focus on the product now. Unlike everything else so far, this is what? This is chiral. That is a stereocenter. So you could have a mixture. Well, you definitely have a mixture of enantiomers, right? Now, with LAH or sodium borohydride, we'll get the racemic, or the DL thing. But if we had a chiral reducing agent, what could we possibly get? We could get what? The enantioselective process. And this is important in biology and industry. Let's go back up to the overhead here and see example of asymmetric reduction. Okay. Back up there, Nick. Yeah, thank you. This so-called Kuori-Bakshi-Shibata reduction, enantioselective ketone reduction. You have to have 2 different things on the ketone here. You can't do this with aldehydes, right? Aldehyde goes to a primary alcohol. Ketones go to a secondary alcohol. Okay. And if you use this chiral catalyst here, this chiral boron catalyst, comes from proline. It has the S form right there, pure form. Boron, borate, it forms a Lewis acid complex, gives the same borate thing. And it reduces here to give 1 enantiomer, the R enantiomer, and 98% enantiomeric excess. That's 99-to-1 ratio over the S. And we can explain why, the mechanism. That's an advanced topic. Don't worry about that. But the concept is if you have something chiral, catalyst-wise, you can get the enantioselective thing. So I'm showing you how it complexes and how the borate gets delivered here. And that's this transition state here. The first S here refers to the S on the catalyst, okay? Giving the R product in this case selectively. Now the R here product and the S product are the same energy, right? They're enantiomers. So how do you get this selectivity? This is the concept you should be aware of. The transition states leading to the 2 enantiomeric products are different. This is creating the R stereocenter in this transition state. This one's creating the S stereocenter in the product. What's the relationship between these 2 transition states? They're diastereomeric. This is the SR, pro-R transition state. This is the S pro S. That's if you flip the ketone around and have a steric clash between this phenyl and this methyl. We could go into more detail here, but this is an advanced topic. But you can see that the diastereomeric relationship here means they can have different energies. And if one's higher than the other, that's the slow one, and it goes more quickly over this transition state to give that product. Okay, that's all you need to know there. Don't worry about the Corey-Bakshi-Shibata catalyst. Don't memorize that. Just the concept of if you have a chiral catalyst, potentially with a ketone, you could get the chiral product. This is seen in biology all over the place. When we get to this later in the semester, and maybe you've heard of this before, these are cofactors and enzymes. So this is nicotinamide dinucleotide hydride or reduced form. It's a dihydropyridine, and this is just part of the cofactor. There's a big adenosine and some other groups down here. So the wiggle here just means, you know, this is the part that's involved in the mechanism. The enzyme's called pyruvate hydrogenase, and here's our substrate, pyruvic acid. Maybe you've heard of that from glycolysis in biology or some other class related to that. Pyruvate goes to lactate. Okay, and so pyruvate's a ketone here. If you push the electrons here, use the electrons on the nitrogen, push the electrons over, and bring a hydride off the pyridine and add it to the ketone. And then within the enzyme, that's what these brackets are. The enzyme grabs both of those. It's a big molecule, right? And then you protonate the oxygen, the minus, okay? And you get lactate. And look, you get only S-lactate from this enzyme. Why? Because this enzyme is chiral. It's an antiopure. It's made up of chiral amino acids, right? So there's two transition states, one going to the S product, one going to the R, but those two transition states are diastereomeric, okay? Also notice the product here of the cofactor is NAD+. Now you have a plus charge on that nitrogen, right? So you can keep track of the formal charges. NADH is also Mother Nature's oxidizing agent. You can go backwards here. NADH is Mother Nature's reducing agent, okay? Hydride coming off, adding the substrate. Same thing. Here you can take that hydride back off and go back to the ketone. You might want to practice that mechanistically, going backwards and forwards. If you master that, you'll have a big leg up in biochemistry 481. Anyway. All right, let's get into these other reactions. We've done sodium borohydride and LAH with these guys. Let's get into some of these other substrates here for LAH and see what we need to know there. Like we said, LAH will be very aggressive and can do other types of derivatives. And let's see if we can do some of those. And then we'd like to review some of the oxidation reactions as well. There's a couple other reagents to keep track of here. Dibol is diisobutyl aluminum hydride. There's two isobutyl groups on dibol, and that's nice. It has an acronym associated with it. This is more mild than LAH. And we also have another milder reagent here. It's called tri-T-butoxy aluminum lithium tri-T-butoxy aluminum hydride, AL, sorry. That doesn't have an acronym, sorry about it. This is specific for esters to stop at an aldehyde. This is specific for acid chlorides to stop at an aldehyde. So let's look at these reactions first with esters. So if we take an ester like this, react it with LAH, quench with water, we'll get the primary alcohol, okay? The byproduct here is ethanol. Sometimes we keep track of that too. If it's a small alcohol, we don't worry about it. But that's the main thing here. Notice that's where the carbonyl is, right there. If we react this reagent instead with dibol, and then quench with water, look at this. We stop at the aldehyde. Okay. And that's kind of a neat reaction. Notice dibol only has one hydride on it, where LAH has 4, right? So that might give you a clue there. The mechanism will bear that out. Now let's see for tri-TB-toxy aluminum. Let's do the same ester here. So LH, we already know that. But if we use lithium, aluminum, tri-TB toxide, and then quench with water, we also stop at the aldehyde. And we'll use this reagent, not for the ester, sorry. Oh, made a mistake. These are different. The acid chloride, okay? This one's specific for the tri-TB-toxy group. You can mix them up. There's some cross-reactivity there, but really Dahl's specifically developed for esters. The more reactive thing, the chloride. And notice there's only one hydride here on tri-TB-toxy aluminum. So again, we just have the one addition going to the aldehyde. This one, you know, also goes to the primary alcohol in that case. Let's get into the mechanism of this enough to figure this out. Shouldn't be too bad. And yeah, hopefully you're seeing some commonality here among the mechanisms. The difference here is with the derivatives, you have the potential leaving group on there. So yeah, let's just look at it like this. So X here, and you've got aluminum, and I'll draw kind of one off here. So the mechanisms are really all the same, only you have what? On your tetrahedral intermediate now, you have the ability to lose that leaving group and what? Generate an aldehyde. The aldehyde is very susceptible, what? To more hydride being added, right? So at that point, you'd have the aluminum like this. You could draw a covalent bond there and have it on there already. And then have it deliver some more. And then what do you have? You have the aluminum H2 and the two hydrides on there. And then when you quench with water, you see, and that's the second step, then the metal oxygen bond grabs a proton off water. And that gives you the product there. Okay. Now with Dibol, it's a little bit different. With Dibol, and that's specific for which one did we say? With esters, okay? So let's maybe have an ester here, okay? And Dibol, you know, has the aluminum, and it has the two isobutyl groups on there. So, you know, how are we going to do this reaction? Well, we can still add our hydride here, bring the electrons up, and we can put the O minus on the aluminum, you see, and a hydride there, okay? So yeah, I kind of combined a couple steps there, but I think electron pushing you can trigger. The important thing is this right here, the adding there. And there are some variations in the book, okay? I'm being actually a little more thorough. The book kind of sloughs over some of the mechanisms, but the key thing is this here, okay? The addition here. You know, it's with sodium borohydride and lithium aluminum hydride, we have the sodium and lithium that can coordinate with the carbonyl first, but we don't have that with Dibol. We have the neutral thing here. But we can do that addition, right? And then what? Well, we can bring the electrons back down and have this come off. And at that point, you see, we don't have any more hydrides on aluminum. We have the isobutyls here. So notice there was only one hydride to begin with here, whereas LAH, look, we had three more here, right? So that's the basis of the chemoselectivity, stopping at the aldehyde, okay, with Dibol, okay? And I think you can see the tri-TB toxide lithium with the chloride is a similar thing there, only then we have, what, a chloride here, and then we have the same thing here. We only have the one hydride. So lithium, aluminum, hydride, tri-TB toxide with acid chloride stopping at the aldehyde is similar here in that we stop at the aldehyde from the ester with Dibol. Don't mix those up. Make sure you link that specifically. Dieballs for esters, just stop at the corresponding aldehyde, and tri-2-butoxy lithium aluminum hydride is specific for the acid chlorides. I think that's all we need to say there on that. Okay, a little bit more on this with LAH. And this is a little bit trickier mechanism, but the concept is the same. LAH, of course, we're using strong hydride reducing agent. And let's look at carboxylic acid now with LAH. Quenching with water, what do we get? Get the primary alcohol. And we can go through that, and you'll see this is potentially a leaving group. It won't come off as OH minus. It'll come off coordinated to a metal, okay? Well, we'll see that. We're adding 2 hydrides here, okay, because we've got 4 on LAH, right? Now, here's the other derivative that's not as reactive. It's an amide. Now, amides have resonance, right? The lone pair into the carbonyl. But amides will react with LAH, okay? I told you it's a very aggressive reagent. Catches fire on a balance, starts to shoot out sparks if you don't deal with it right away. Does it give the alcohol too? It looks like it could, right? But no, you have an amine on there, right? It actually gives the amine. Okay. How does it give the amine product? Well, we need to look at the mechanism a little bit here. So let's see. Let's take LAH, hydride. Take 1 hydride, and we're going to eliminate a molecule of hydrogen gas. That adds to the danger, right? If you get a spark in the presence of hydrogen, you're going to get an explosion. Okay? So you got to keep this away from anything dangerous there. But at that point, you have what? You have this with the aluminum, and 3 still on there. Okay. And what do you get now? Well, add the hydride. Push the electrons up. So yeah, it's, the same here. Hydrogen, aluminum. Okay. It's a little bit different though. And this thing, this is a proton source now, right? So a little bit of a variation there. Not much though. Add this in, and what do we get here? We have a leaving group, but it's coordinated to metal. It's not hydroxide coming off. And what do we get? We get the aldehyde, and we get O minus aluminum H. Okay. Well, that can add to the aluminum again. It's still Lewis acidic, right? So what do we get? Oh, aluminum H2 O minus minus plus charge. Have another hydride add. And yeah, this mechanism's more complicated, isn't it? Aluminum O minus H, and H is on there. Okay. And you see we've added the second one right there, right? Here's the first one. I should have put that on there, I guess. There's 2 on there now. And then how do we get rid of that? Well, that's when you add the water and protonate, and you get the primary alcohol. Okay. Not too bad, but the variation being generation of some hydrogen gas. And our leaving group is a metal oxide, not hydroxide. Okay. Now let's see how we can rationalize this amine story. How do we form an amine from this here? Well, got a little bit different thing here. We've got the amide. And is the amide acidic enough to donate a proton to aluminum hydride? And the answer is yes. Okay. And we're going to get this here. and the electrons can come up, and we'll get this nitrogen with O minus there. And I'm just going to put that on the aluminum guy there. And notice that gives us what? Another byproduct of H2. Okay. The pKa of an amide like this is about 35, or no, 25. It's not very acidic at all. But once you do grab the proton off, it does resonate up there. Give that type of intermediate. Then we can take a hydride, add it here. And notice that will give us reduced form and nitrogen and 2 lone pairs there. B minus charged. Okay. And that's okay. Because what this is going to do then, these will come back down, and we have a leaving group here, which is again aluminum oxide. Sorry, this H2. Yeah, one came off there. Hopefully I'm right there. Okay, any errors? There might be some errors here. The key thing is the addition of the hydride right here, okay? And that gives us this. But you see, we can break down our tetrahedral intermediate. We have this as the leaving group. Now, why is that the leaving group? Well, aluminum oxide, okay? That's a mineral, component of mineral, of rocks, right? Aluminum oxides. That's how aluminum is in nature. That's a very strong bond. So having this come off, you see, this will give us what? This nitrogen carbon double bond now with O minus aluminum 2, okay? Now, we could do a complex here with the Lewis acidic aluminum. That would look like this, right? Hydrogen, and yeah, plus charge there. And so now look what we can do. There's our amine, finally. We have to add 2 hydrides again. That gives us the second one on there, the nitrogen, and aluminum's still on there temporarily. See, it's neutral now. At this point, it would be negatively charged. And then how do we get the amine off? Well, water, when we quench, that protonates this bond, and we get the amine. Okay, amine product. And yeah, those are tough mechanisms, I agree. But what do they have in common? The hydride additions, right? A little bit different leaving group, whatever, but the hydride going on to give us the product. So amides go to amines. Okay, let's review that here on the chart. Then we'll do a little bit on oxidation, but I think we did the rest of these. We did carboxylic acids, esters, acid chlorides, and amides going to amines. That's a different one. You see, all these others, look at that, all the others go to alcohols with LAH, right? And then we have sodium borohydride, which is milder, limited just to aldehydes and ketones. Yeah, real diversity here, but all the reagents are the same. They're hydrides, right? H minus, you could say. The diversity is in the different types of carbonyls. A lot of the products are similar, okay? But you keep track of them by the mechanism, I think. And then the milder things here for the acid chloride to go to aldehyde, and then for the ester with diol. Sometimes it's written as diol H to go to the aldehyde. All right, let's look at oxidation reactions. And this won't be much. This is a minor topic in this chapter, but oxidation means going in the other direction from the alcohol to the carbonyl, okay? And we've already seen this in some cases, right? We've seen this, where we've taken chromic acid with a primary alcohol, okay, back to what? Carboxylic acid, okay? Notice the 2 reactions are now complementary. How do we go back? LAH, okay? And that's another way to study these reactions. This one, you see, has oxygens on it. It's going to do an oxidation, okay? This has hydrides on it. It's going to do what? A reduction, okay? that's a way to keep track of those. Uh, if we have a secondary alcohol, we'll go to what? With chromic acid, we'll go to the ketone. Okay. If we want to stop at the aldehyde, I'm sorry, let's do primary alcohol here, 1-butanol. What if we want to stop at the aldehyde? Now, if we added chromic acid, we'd go all the way to the carboxylic acid. But again, we have a milder reagent here, right? Anybody remember what that was? That's also from 351, pyridinium chlorochromate. Now, I'm not going to draw out that reagent again, but it's a chromate, but it has a chlorine on there, which attenuates the reactivity, and it stops at the aldehyde, okay? So that's another thing to go. Keep track of. And again, the other direction with sodium borohydride or lithium aluminum hydride would be the reduction part here. Now, the only new reagent here is this one. You can have an aldehyde, an alcohol. Both of these can be oxidized, right? The aldehyde could be further oxidized, like with chromic acid, all the way to the carboxylic acid here. The secondary alcohol could also be oxidized to a ketone. And indeed, if you used chromic acid here, okay, you use that reagent, you would go very quickly to both of these being oxidized, okay? Those are two different functional groups though, right? The aldehyde becoming a carboxylic acid and the secondary alcohol becoming a ketone. But what if you wanted to stop at this, the alcohol acid? Now this reaction I'm going to show you is the new one in this chapter. All these others are actually stuff we've already covered now, adding in the LAH reaction. What if we want to chemoselectively oxidize the aldehyde to the carboxylic acid and leave behind the alcohol here? Well, we can do that. It's a reagent called silver oxide. Silver is Ag. Where does that come from in the periodic table, by the way? Argentum, the Latin term. And you can think of what country is a source of a lot of silver mining. In fact, the name of this country means AG there. Argentina, very good. Argentum, Argentina, meaning the silver mines there. So that's how I remember it, AG. But it has the oxygen on it, so it can do oxidations, but it's mild, okay? It's just a silver oxide. Sometimes we have it with ammonium hydroxide. This is so-called Tollens reaction. And it's specific for aldehydes to go to carboxylic acids. And notice it doesn't have enough oxidizing power to deal with alcohols. That'll be important for sugar chemistry coming up. And we'll show you this Tollens reaction later on. Questions on these oxidations? I think we'll leave it at that. Pyridinium chlorochromate, should we write that out again? Do you remember what that looks like? Chromium, chlorochromate, minus, and then it has a pyridine in there. One of the P's stands for pyridinium. So it's actually a salt between this chlorochromate and the pyridine. Okay, so that is PCC. Okay, it's a salt. And it's nice because you can easily weigh it out. And look, there's no OH here. It's not a corrosive material like the chromic acid. That's as strong as acid as sulfuric acid. In fact, we make this with sulfuric acid and the chromate salt. But PCC is nice because there's one less oxygen, and that's another way to remember it. One less oxygen means it'll only do the one oxidation. There you go. A good way to remember it. But know the structure at least. I won't expect you to know the mechanisms. I could show you the mechanisms of how these chromate things work, but yeah. Maybe we'll review that when we do sugars, when we talk about that. But again, these are oxidations, right? We're taking off hydrogen, going to that. Secondary alcohols also with PCC can also be oxidized to ketones. But the key thing with PCC is primary alcohols going to aldehydes. Okay, no mechanisms needed there. We gave you enough mechanisms today, didn't we? Okay, that would be cruel punishment if I threw in the mechanisms of the chromates, so we won't do that. But now, the key thing for Tuesday will be the Grignard reagents. So make sure you're read ahead to the organometallics now. It'll be a similar type of reaction. The mechanisms will be very similar, but instead of hydride as our nucleophiles, we'll be using what? Carbanions. Carbon with pairs of electrons as nucleophiles. So we'll be making carbon-carbon bonds, which are much more important synthetically than these reducing agents. These are important reactions, but not nearly as important as the Grignards coming up next week. So remember, no class on Monday. We'll see you on Tuesday. Any questions? Or if you're here live, you can always come down and ask questions or send me questions by email, and we can help you out with that. All right, very good. We'll see you next week.